Good morning, everyone. Today we're going to talk about something very relevant in our digital world, the web application attacks. Every time we log into a website, submit a form, or shop online, there are potential threats lurking. We look at five major attack types: cross-site scripting, SQL injection, cross-site request forgery, information leakage, and session hijacking. For each one, we'll break down how it works, the actual technique, and we'll look at real cases where these attacks happen in the real world. So, before we dive into each attack individually, let's set the stage. So, web applications are complex systems. They handle our personal data, financial transactions, private messages. This makes them high value targets. So, the five attacks we're covering are consistently ranked in the OWASP Top 10, the industry standard list of the most critical web security risks. So each one targets a different weak point. Some attack the user, some attack the database, some attack the communication between user and server. So understanding them is the first step to defending against them. Okay, so first is the cross-site scripting or XSS. So XSS is about injecting malicious JavaScript into a web page so that when other users visit the page, the script runs in their browser, not the attackers. Think of it as a living a booby trap on a website. So there are three types of XSS. The stored XSS is the most dangerous one. The malicious script is saved in the website's database and served to the every visitor. Reflected XSS when the script is embedded in a URL. So you click a link, then the script bounces off the server and runs in your browser. So the second one is the DOM-based XSS. It manipulates the page content directly in the browser without going through the server. So for the example payload you see here as the one, this script silently sets that the victim session cookie to the attacker server. With that cookie, the attacker can impersonate the user. So we have according to research, we have the real world cases. In 2018, British Airways suffered a devastating XS attacks. Attackers compromised a third-party JavaScript library used by the BA website. So they modified it to silently copy credit card numbers and personal details as customers typed them during checkout. So this was active for 2 full weeks before anyone noticed. So there are 500,000 customers were affected. British Airways was fined 20 million under GDPR. This is a perfect example of why you can't just trust third-party scripts. So prevention comes down to output encoding. Never let raw user input the treated code, content security policy headers, and marking session cookie as HTTP only. So JavaScript can't access them. So the second one is the SQL injection. So SQL injection is one of the oldest attacks, yet it's still the most common. So the idea is simple. Instead of entering a normal username, an attacker type a SQL code into a login from a search box. If the application isn't properly built, the SQL code gets executed by the database. So there are three variants. The inbound SQLi gives result directly on the page, so attacker can use union statement to pull data from any table. So blind SQL data is a stealthier. The attacker asks yes or no question to the database by watching for true or false responses. The third one is the outbound SQLi. It sends stolen data to an external server controlled by the attacker. So the classic example on screen, if you enter admin dash dash as a username, then the double dash comment out the rest of the SQL query. So including the password check, you log in without knowing the password, So there are example real world cases. So according to research, in 2008, Heartland Payment Systems, one of the largest credit card processors in the US, so was breached via the SQL injection. So attackers used it to gain access to the system that planted malware to capture and the data as it traveled through the network. The result, 130 million credit card numbers stolen Heartland paid $145 million in compensation at the time. It was the largest data breach in history. So the fix is surprisingly simple. Uh, Parameterize queries or use prepared statements. So this separates the SQL code from the user input. So injected code is never treated as a command. So the third one is the cross-site request forgery or the SCRF. So CSRF is a clever attack because it doesn't steal your password. It tricks your browser into doing things without your knowledge or while you are logged in somewhere. So here is the scenario. You log in into your bank and you're authenticated. So without logging out, you visit another tab. So maybe a malicious link from an email. So the malicious page contains hidden code like an image tag that automatically sends a request to your bank. So your bank sees the request, sees your session cookies are attached, think it's you, and process it. So the image tag with SRC pointing to back transfer URL. So your browser tries to load the image but actually executes a transfer. Yes. So there are real world cases here. The two notable legal cases from around 2007 and 2008. The ING Direct, an online bank, and Gmail both suffered the CSRF, with ING attackers were able to trigger unauthorized money transfer from victims' accounts simply by having them visit a crafted page. With Gmail attackers, silently add email forwarding rules, so every email the victim received was also sent to the attacker. So both cases demonstrate that CSRF can be catastrophic without leaving obvious traces. The user doesn't see anything happen. So how we can prevent it? So CSRF tokens, a unique secret value included in every sensitive form. The server checks for it. If it's missing or wrong, the request is rejected. So the same site cookie attribute also helps by restricting when cookies are sent cross-site. Okay, the next one is the information leakage. So what is information leakage? It is a bit different. It's less about actively attacking a system and more about what the system accidentally reveals. So it's often the first step an attacker takes before launching a bigger attack. So it becomes in many forms. Verbose error messages are the most common. If your website crashes and shows a full stack trace with the database names and file paths, you've just handed an attacker a map of your system. Directory listing means your browser or the web server shows a list of all its files when no index file exists. So unprotected APIs might return far more data than the app needs, like returning a full user's object when the only name was needed. And sometimes sensitive info like API tokens or password ends up in URLs or log files. The example error message on screen, it is the MySQL error, tells the attacker which database is in use and the exact table name. So that's the valuable recon. So example real-world cases, the Cambridge Analytica scandal in 2018 is a prime example of information leakage at scale. Facebook APIs was designed with overlay permissive data access. Third-party apps could not only access the installing user's data, but also the data of all of their Facebook friends. Without those friends' knowledge or consent, a personality quiz app exploited this to collect data on 87 million people. Cambridge Analytica then used this data to targeted political advertising. So Facebook was fined a $5 billion by the FTC. So what is the reason of this? Minimize what data your system exposes, only return what's needed, validate API access, and never let error messages reveal internal system details. So one is session hijacking. So when you log in into a website, the server gives your browser a session token. Usually, it's stored as a cookie. It's like a temporary ID badge. As long as you hold it, the site recognizes you. Session hijacking means the attacker steals that badge. The methods vary. Session sniffing on an unencrypted HTTP connection. So the attacker enters the network a traffic and reads the cookie directly. So XSS assisted thief. So you see a script to exfiltrate document cookie to the attacker server. So session fixation. So the attacker sets the session ID before you log in. So when you authenticate, your session is already known to the attacker. So this is the most common or familiar one, the man in the middle. The attacker position themselves between you and the server and intercept everything. The code snippet. The one line sends the victim entire cookie string to the attacker's domain. So example, real world cases. In 2010, security researchers Eric Butler released a Firefox extension called the Fireship to demonstrate session hijacking. He pointed it at open Wi-Fi networks like coffee shops, and it automatically sniffed HTTP traffic and captured session cookies for major sites like Facebook, Twitter, and Amazon. Anyone in the same coffee shop could click a button and instantly log in as another user on those sites. So it was mean as a wake-up call, and it worked. So the release of Fireship directly accelerated the industry-wide adoption of HTTPS. So what is the prevention here? So to enforce the HTTPS, everywhere using the HSDS headers, so cookies are always encrypted in transit. Set the secure and HTTP only flags on the session cookies and regenerate the session ID immediately after login. So as you can see the comparison table, let's take a step back and compare all 5 attacks side by side. So this table summarizes the target, technique, goal, and key prevention for each one. Notice that XSS and session hijacking are closely related. XSS is often used as a stepping stone to hijack session. SQL injection directly targets the database, while a CSRF exploits the trust to the server has in the user browser. Information leakage is the most passive but enables all the others. Every attack has a clear technical countermeasure. The challenge is consistently applying them throughout development. Okay, so here are the key takes away. So what do we take away from all of this? First is all these attacks exploit some form of trust, either trust in user input, trust in session, or trust in an API. If you design your system to be skeptical and validate everything, you significantly reduce your attack surface. Second is information leakage is often the opening move, so attackers gather intel before striking. So locking down what your application reveals limit their ability to plan. Third is defense in depth. No single security measure is enough. You need layers, input validation, HTTPS, content security policy, and the CSRF tokens, and the continuous monitoring working together. So and finally, so these aren't theoretical threats. British Airways, Heartland, Facebook, Gmail, these are real organizations that paid enormous financial and reputational costs. Security is not optional, as the code says that security is not a product. It is a continuous process. Thank you.